Ladies and gentlemen, when you hear the word explosion, your mind jumps straight to failure, danger, and disaster. But what if the moment everyone is calling a breakdown is actually proof of something working exactly as designed? What if the most viral footage you've seen is not a warning sign, but a window into how the future of transportation handles extreme energy under extreme pressure? In the next few moments, we're going to separate fear from physics, headlines from hard data, and perception from reality, because what actually happened with the Cybertruck isn't what most people think. And once you understand it, you'll never look at electric vehicles the same way again. And what actually happened with the Cybertruck explosion is a story shaped by engineering, reality, public perception, and how innovation behaves when pushed to its limits. From the outside, the word explosion creates an image of catastrophic failure, but inside the system, the event reflects how advanced electric vehicle safety is designed to respond under extreme and abnormal conditions. Every component of the Cybertruck was built with first principles thinking, meaning nothing was assumed, and everything was engineered from the ground up to handle scenarios that conventional vehicles were never designed to survive. And the Cybertruck uses a structural battery architecture where the battery pack is not just a power source, but a load-bearing part of the vehicle. This design reduces weight, increases rigidity, and improves safety by distributing forces across the entire structure. In rare cases involving severe impact, external fire, or experimental stress testing, lithium-ion cells can enter a state known as thermal runaway. When this happens, energy is rapidly released, producing heat pressure, and sometimes visible flames or explosive sounds. What matters is not that energy is released, but how it is controlled. And in the Cybertruck, energy release pathways are engineered to vent outward and away from the passenger cabin. This means that what appears dramatic on camera is often the system doing exactly what it was designed to do: redirecting force, isolating cells, and preventing a chain reaction. Traditional vehicles carry flammable liquid fuel, which can ignite unpredictably. In contrast, electric vehicles manage energy through software, hardware, and physical separation, allowing failures to be measurable, contained, and studied in detail. And the stainless steel exoskeleton of the Cybertruck plays a critical role in these scenarios. Unlike conventional crumple zones that absorb energy by collapsing inward, the exoskeleton redistributes impact forces across the body. This can change how damage appears externally. Instead of gradual deformation, energy is transferred rapidly, which can make an incident look more severe than it actually is from a safety perspective. Visual intensity does not equal passenger risk, and that distinction is often lost in viral clips and headlines. And every reported incident triggers a deep internal analysis. Data from sensors, battery management systems, and onboard computers is reviewed frame by frame. Temperature changes, voltage, behavior, structural stress, and software responses are reconstructed to understand exactly what occurred. This feedback loop is central to the company's philosophy. Failure is not hidden or ignored. It is measured, learned from, and used to refine future designs at scale. And it is also important to separate controlled testing events from real-world accidents. Some explosions occur during extreme validation tests, designed to exceed any realistic road scenario. These tests exist precisely to expose weaknesses before vehicles ever reach customers. When such footage surfaces without context, it can be misinterpreted as a flaw rather than proof of rigorous safety margins being explored and reinforced. And public reaction often focuses on novelty. The Cybertruck looks unlike anything else on the road, so any incident involving it attracts disproportionate attention. Similar events involving conventional vehicles rarely generate the same scrutiny despite occurring far more frequently. Innovation tends to amplify perception, especially when it challenges long-standing assumptions about how vehicles should look and behave. And what actually happened when examined beyond the surface is a demonstration of controlled energy management, not uncontrolled destruction. The systems responded as engineered, the structure performed its role, and the data gathered feeds directly into continuous improvement. This is how progress works when speed, safety, and scale intersect. The Cybertruck was never meant to fit comfortably into old categories, and moments like these reveal not weakness, but the reality of pushing transportation technology into new territory where every extreme outcome becomes another data point driving the next iteration forward. And that next iteration forward depends on an uncompromising relationship with physics, materials, science, and real-world feedback. Electric vehicles do not behave like combustion vehicles under stress, and expecting them to do so is a misunderstanding of how energy systems evolve. When a high-density battery system is pushed beyond its safe operating envelope, It responds according to electrochemical laws, not marketing narratives. The difference is that these responses are observable, traceable, and improvable, rather than hidden behind decades of normalized risk. And the Cybertruck's battery management system constantly monitors thousands of data points every second. Cell temperature, internal resistance, charge balance, and structural load are all evaluated in real time. When an abnormal condition begins to develop, the system prioritizes isolation and containment. Modules are separated electronically and physically, limiting propagation. This is why, even in rare extreme events, the outcome is localized rather than systemic. What may look like a sudden explosion is often the final stage of a controlled release after multiple safety layers have already done their job. And the stainless steel structure also changes how heat behaves during these events. Unlike painted steel or aluminum panels, the alloy skin does not burn, melt easily, or release toxic fumes. It acts as a shield, reflecting and dissipating thermal energy, while maintaining structural integrity longer than traditional body materials. This gives occupants more time, emergency responders clearer access, and engineers a more predictable failure profile to study and refine. And another factor often overlooked is how modern vehicles are evaluated in the age of instant media. A few seconds of footage stripped of telemetry, context, and environmental conditions becomes a narrative. In reality, every serious incident is reconstructed digitally. Engineers can replay the event with precision down to the millisecond, understanding not only what failed but why it failed in that exact sequence. This ability to learn rapidly is what accelerates safety improvements far beyond what legacy automotive development cycles could achieve. And the Cybertruck was designed not just as a vehicle but as a platform. Software updates can change thermal thresholds, charging behavior, and energy distribution strategies without altering physical components. That means lessons learned from one incident can be applied across an entire fleet almost instantly. This is fundamentally different from traditional recalls that require mechanical retrofits over months or years. Safety is no longer static. It evolves continuously with data. And it is also important to understand the role of edge cases. Vehicles are tested far beyond normal use, including scenarios that most drivers will never encounter. These include extreme impacts, prolonged exposure to fire, and deliberate overstressing of systems. When an event occurs at the boundary of these tests, it does not represent everyday risk. Instead, it confirms that the boundary exists, that it was anticipated, and that it can now be pushed even further outward through design refinement. And the conversation around explosions often ignores scale. Millions of miles are driven every day without incident, silently validating the design. The rare moments that do surface become focal points precisely because they are rare. If electric vehicles were inherently unstable, the data would show it clearly and consistently. Instead, the trend points toward lower overall fire risk compared to combustion vehicles, despite higher scrutiny and visibility. And the Cybertruck's unconventional shape and materials also invite assumptions that do not apply. Flat planes, sharp angles, and rigid surfaces change how forces travel through the vehicle. This can produce unexpected external results while maintaining internal safety. Traditional intuition about crumpling, bending, and tearing does not map cleanly onto an exoskeleton-based design. Understanding this requires letting go of familiar visual cues and trusting measured outcomes instead. And what continues to matter most is not whether an extreme event looks dramatic, but whether systems behave predictably, passengers were protected, and knowledge was gained. Each data point feeds into simulation models, manufacturing adjustments, and software logic. Over time, this feedback loop reduces risk further, not just for one model but for every future product built on the same principles. And this approach reflects a broader philosophy. Progress is not the absence of failure, but the speed and transparency with which failure is understood and addressed. The Cybertruck exists at the intersection of radical design and real-world constraints, and incidents, however rare, are part of that learning curve. The result is not stagnation or retreat, but refinement, iteration, and a clearer understanding of how to manage immense amounts of energy safely, efficiently, and predictably as transportation continues to move toward an electric future driven by data rather than assumptions, and assumptions give way to measured evidence collected at scale. The narrative around safety changes from fear-based speculation to engineering-driven clarity. Electric vehicles operate within known physical limits, and those limits are continuously mapped, tested, and expanded. Each anomaly adds resolution to that map. Rather than treating rare incidents as setbacks, they become inputs, strengthening the system as a whole. This mindset is fundamental to how complex technology matures under real-world pressure. And the Cybertruck's development embraced this reality from the earliest prototypes. Materials were chosen not for tradition but for performance under stress. Manufacturing techniques were redesigned to reduce variables and improve repeatability. Even the way the vehicle is assembled reflects an intent to minimize weak points where energy could concentrate unpredictably. When an extreme event occurs, the outcome is not random. It follows pathways defined by design choices, and those pathways can be adjusted with precision. And battery chemistry itself continues to evolve. Cell formulation separators and cooling strategies are refined constantly to increase stability and reduce the likelihood of thermal escalation. The Cybertruck benefits from lessons learned across an entire ecosystem of vehicle storage products and grid-scale systems operating globally. This cross-domain learning accelerates progress in a way isolated development never could. What happens in one context improves safety everywhere else. And there is also a human factor often missing from public discussion. Emergency response protocols for electric vehicles are different, and training has expanded alongside adoption. First responders now have access to clear guidance on how to approach high-voltage systems safely. Vehicles are designed with visible cut points, reinforced structures, and predictable shutdown behavior to support these responders. In extreme cases, this coordination matters as much as the hardware itself. And another misconception centers on energy density. While electric vehicles store large amounts of energy, they do so in distributed form. Thousands of small cells share the load rather than a single concentrated reservoir. This distribution allows for granular control and isolation. When one part of the system is compromised, it does not automatically compromise the whole. This architecture is a core reason why incidents remain contained even under severe conditions. And the Cybertruck software layer adds another dimension. Algorithms adapt to usage patterns, environmental conditions, and aging components. As the vehicle learns, it can adjust margins, dynamically reducing stress on components over time. This adaptability means safety improves not only with new models, but with vehicles already on the road. The fleet becomes safer collectively as data accumulates. And public trust is built through consistency, not perfection. No transportation system has ever achieved zero incidents. What differentiates advanced systems is how predictably they fail and how quickly they improve afterward. The visibility of electric vehicle incidents can distort perception, but it also forces accountability and transparency. Every event is documented, analyzed, and addressed in a way that leaves an auditable trail of improvement. And the Cybertruck challenges expectations not just in appearance but in how it reframes risk. It invites a shift away from intuition shaped by legacy vehicles toward understanding grounded in data. This shift takes time. It requires repeated exposure to evidence that contradicts long-held beliefs. Over time, those beliefs adjust, and what once seemed alarming becomes understood as manageable and increasingly rare. And as adoption grows, the statistical picture becomes clearer. Larger sample sizes reduce noise and reveal true trends. Those trends show continuous improvement in safety metrics, reliability, and durability. Each generation builds on the last not through cosmetic changes, but through deeper integration of hardware, software, and manufacturing insight. The Cybertruck sits within this trajectory, benefiting from years of cumulative learning, while contributing new data of its own. And what ultimately defines progress is alignment with reality. Energy behaves according to physics, materials respond according to their properties, and systems improve according to how well they are observed and adjusted. The Cybertruck story, including moments of extreme stress, reflects this alignment. It is not about eliminating all risk, but about understanding it so thoroughly that it can be managed, reduced, and communicated honestly. And in this context, isolated footage loses its power. What remains is a broader pattern of disciplined iteration where every outcome feeds forward into better design. The vehicle continues to evolve alongside the infrastructure, regulations, and user behavior that surround it. Together, these elements form a feedback loop that steadily raises the baseline for what safety and performance mean in an electric age driven by evidence rather than assumptions, and this ongoing cycle reinforces a core principle. Visibility creates accountability, and accountability accelerates improvement. Every component of the Cybertruck is designed with traceability in mind, from raw material sourcing to final assembly and long-term operation. When an extreme event occurs, it is not treated as an isolated anomaly, but as part of a larger dataset. Patterns emerge over time, allowing engineers to distinguish between one-off anomalies and systemic signals that require design changes. And manufacturing precision plays a critical role in this process. The Cybertruck's production methods reduce part count, eliminate unnecessary complexity, and tighten tolerances. Fewer parts mean fewer failure points, and tighter tolerances mean more predictable behavior under stress. When energy is released, it follows known paths rather than improvising new ones. Predictability is a cornerstone of safety, even when outcomes appear dramatic from the outside. And the vehicle's thermal architecture is another layer often misunderstood. Cooling channels, heat sinks, and structural interfaces are designed to move heat away from critical areas efficiently. In abnormal conditions, these same pathways help control temperature spikes, slowing escalation and buying time for protective systems to respond. This layered defense strategy is intentional. No single component is relied upon to prevent failure. Instead, multiple systems overlap, each capable of mitigating risk independently. And as real-world data accumulates, simulation models grow more accurate. Virtual testing environments can now replicate complex interactions between structure, battery, software, and environment with increasing fidelity. This allows future designs to anticipate scenarios that were once impossible to model. The Cybertruck contributes to this expanding library of knowledge, informing not just incremental updates, but entirely new approaches to vehicle architecture. And another dimension of progress lies in user behavior. Drivers interact differently with electric vehicles compared to traditional ones. Acceleration profiles, charging habits, and load distribution all influence system stress. Software adapts to these behaviors, smoothing peaks and reducing wear. Over time, the vehicle becomes better aligned with how it is actually used, not how it was assumed to be used. This feedback loop further reduces the likelihood of extreme outcomes. And regulatory frameworks are evolving alongside the technology. Safety standards originally written for combustion vehicles are being updated to reflect electric architectures. Data-driven insights from vehicles like the Cybertruck inform these updates, helping regulators base decisions on evidence rather than analogy. This alignment between engineering reality and policy improves outcomes across the entire industry. And public understanding lags behind technical progress, but it does move. Early skepticism gives way to familiarity as new technologies prove themselves repeatedly. Incidents that once dominated headlines become footnotes as context improves and comparative data becomes widely available. What remains is a clearer picture of relative risk grounded in numbers rather than narratives. And the Cybertruck's role in this transition is amplified by its visibility. Its unconventional design makes it a focal point for discussion, criticism, and analysis. While this increases scrutiny, it also accelerates learning. More eyes mean more questions, and more questions drive deeper investigation. This pressure sharpens the engineering process rather than weakening it. And long-term durability is another factor shaping perception. Vehicles are not judged solely by how they perform when new, but by how they age. Continuous monitoring allows degradation patterns to be identified early. Adjustments to charging curves, thermal limits, and power delivery can extend component life and reduce stress accumulation. Safety improves not just at the moment of an incident, but across the entire lifespan of the vehicle. And as fleets grow, collective intelligence emerges. Individual vehicles contribute data, but the value multiplies when aggregated. Rare events become statistically meaningful, enabling proactive design changes rather than reactive fixes. This scale advantage is difficult to replicate without deeply integrated hardware and software systems working together. And the broader implication is that transportation safety is no longer static. It is dynamic, responsive, and increasingly predictive. The Cybertruck exists within this paradigm shift, serving as both a product and a learning system. Its experiences inform future designs, which in turn feed back into the ecosystem, raising standards across the board. And what unfolds over time is not a story of isolated incidents, but of convergence toward higher reliability. Each refinement narrows the gap between theoretical limits and real-world performance. Energy becomes more controllable, structures more resilient, and responses more precise. The path forward is defined by iteration, transparency, and relentless alignment with physical reality, ensuring that progress continues to compound through disciplined engineering rather than assumptions.